bullshit.
I don't know everybody.
What?
I don't know everybody. No.
Okay, yeah, sorry. Let's do a quick round here.
I'm Sydney.
Lavina.
Oh, you're right.
See my face.
Oh, Olivia. Cool.
Lou.
Now I know everybody.
Noah.
Now I know everybody.
Jeff.
No, that's wrong. Incorrect. Wrong answer, Dr.
Oh no! Already?
Jeez.
I don't know anything. So we're recording? Yes. Beautiful, beautiful. Hey, I just wanted to check your calc skills real quick.
I'm just woke up.
Oh, you're gonna wake up, all right.
I missed you too. Oh.
Let's see. Let me do the graph so that we can, contemplate what kind of madness this might be.
Dr. She doesn't mess around.
No, we don't.
It's in there.
We did not fuck around.
No, absolutely not.
I thought this was complex analysis.
Maybe on Wednesday. Wednesday, Dr. Chief.
Yes. Somebody question? Oh, I thought so. Okay. This is so fun. I was just so looking forward to being here with you all.
Does that cross out one?
That is actually, where does that cross? Somebody tell me. Uh-oh.
Pi over 2.
Yeah, pi. Let's try pi.
Oh.
That's so
Cosine of pi is 0. And the limit as x approaches 0 of sine of x over x is 1. So that's why it's going to 1 right there. And I'm not going to make you suffer too long. I just wanted you to kind of go, oh yeah, math stuff. Thinking and so forth. So I'm just gonna tell you, if you get this, you did it wrong.
Cool.
So the answer is pi over 2. You can't do that with the calculus you've learned.
No UDVs.
No, nothing. There's nothing you've learned in Calc 1, 2, or 3 that can possibly do that integral. So, good job that you didn't do it. Good job that you didn't come in and cancel these x's and just have the word sine and evaluate that from 0 to infinity and get God knows what. I'm so glad that didn't happen. Let me ask you another one. What about, could you prove this?
Prove it? That's not a word I like to hear.
Oh. You know that identity, the sum of two angles? Any idea how to prove that?
No, I just use it to prevent.
Right, yeah, it's an awesome result, right? We as mathematicians, that's in our little pocketbook. We should be pulling that out when we need it. But proving that is really hard. Because trig is hard. Because you gotta get triangles and stuff and get into the nitty gritty. So this we can't do with anything we've ever learned. This we can't do with anything we've ever learned. But I want to tell you that by the end of this course, you will be able to do both of these in moments. Moments. So the things we're going to talk about in this class are the undercurrents of mathematics. We are literally getting under the hood that you never even knew was a hood. It's like, oh my God, that opens? Wow. And you open it up, and there's this box of insight and mystery and power. That's what this class is. And it sounds like let's see, so who's taking this, or probably you might be taking this. Yeah.
That was so much fun.
I don't think so.
Oh, it was so much fun.
Yeah, I know some of you had it, yeah, some of you, a few of you chilled with me, a few of you
I
have
had cyber for that.
Yes, to
Yeah.
the drama.
it.
Was it
Drama,
traumatic if you distracted him for long enough?
which happened every class, right?
Yeah, that's what I was there for.
Okay.
You should have, if Hugo's in this class, we could go for days without doing anything.
Yeah, I had I was trying to get Hugo into this class, and I started hearing stories about Hugo, and I'm thinking, I think we're okay.
It's worse in combination with me. We play off each other really well.
Yeah, I mean, I love Hugo, but like I heard he's distractor. And then had Trinity been here, and Hugo, I heard that would have been.
No, they don't play together
love
well.
Trinity.
No.
I hope Trinity's doing well.
I'm sure she's doing great. She's doing great. I saw a picture of her in a hobbit hole
Oh.
on Instagram.
No.
Apparently not.
They don't get along. You can ask Hugo that sometime.
So you got this class. This sounds like it's a lot harder than that.
Yeah.
Cause, that word. This class is easier than that class.
That's relative.
No, well, yeah. Most classes are easier than real analysis. But when I took this class, it blew my mind in grad school because it's all about geometry underneath. It's incredible. Like this class is like geometry to the nth power. But in the end, it's very geometric, and we're going to take very geometric approaches to everything in here. So you're going to be drawing lots of pictures, which you can't do here. You can draw pictures, but they're lies. Every picture you draw in real analysis, except for, well, even the real line is a lie. So let's kind of get into it. So first off, I don't have the syllabus with me today. I'll have it Wednesday. It doesn't matter, really. If you know me, you probably trust me and know that I'm going to take good care of you.
Yep.
So, but here's the basics of the class. 60% of your grade is homework, 20% for a midterm, 20% for a final. And we will have exams. Sometimes I've learned the lesson that I should never try to have 3 exams in a class. I can't do it. I just can't freaking do it. So we're gonna have just 2 exams, and they'll be basic skills. So if you haven't had a class with me before, my exams are super basic skills. The homework is where you will suffer greatly, but so goodly. Such good suffering. I mean, you're here to suffer mathematically. That's why you're a mathematician. So, he says it's a baby. So what have you heard about complex number? I'm curious, like what is a complex number? I just want to see where we're at, and then
It's a 2D number where I represents the square root of -1, and it can be used to represent a rotation sometimes.
Cool. Some good knowledge there. Why do we have them?
Because this solution for the 4 degree quadratic sometimes gave you square roots of negatives, but it worked out.
Even more simply, right? Like,
Yeah.
so like the classic story you hear is the number I, which we define as the square root of -1, is needed so that we can solve equations. So we can solve this, a simple quadratic equation, right? Like this, right? So I would go, I'd take the square root of each side, and since I did that, I do my plus or minus. So just the flow of the algebra reveals that. And then we say, oh, well, what is that? Well, let's just, I don't know, just call it something. Now we're done. So that's the story you often hear. But the story is actually way more interesting than that. And so I'm going to ask you to do a little reading before the next class. We're going to have 2 textbooks. This is your main textbook. It's free. I got a print copy. You can actually order a cheap print copy on Amazon if you like print copies. Otherwise, it's available online for free. The other book we have is available for on free, and it's a complex, and this, I've got links to this stuff in the World Class page, but complex-analysis.com. I found this over the summer. This place is cool, and this is going to help you gain intuition about complex numbers. They've got like all these apps you can move stuff. It's so freaking cool. It's just fun. Like I want to go play with it now, but I want to get to this stuff done first. So this is like your second textbook to gain intuition. This is the textbook we'll do problems out of and read to gain super detailed insight. So if you could, please, friends, I would like you to just read, so start reading Beck, and that's 1-1 through 1-3. And if you can maybe try to get through this by like Sunday, the next, like come in Monday, maybe have this at least digested somewhat. Some of it's gonna be like, I need help digesting, can you cut this for me? And it's like, absolutely, I'll feed it to you with a little fork and everything. And then your homework assignment, this is going to be due, so it's homework 1, it's gonna be due next Monday. It's very small. I'm gonna try to do smaller weekly assignments so that they're not some of the beasts I tend to like produce that take 2 weeks from time to time. Due next Monday is from Beck. So anytime I give you homework, it's from Beck, and that's going to be 1, 1, 1, 2, just A and B, 1, 3, C and D, 1, 4, 1, 5, 1, 9, and 1, 11, C and D. That looks like a lot, but they're like simple, these are just like computations with complex numbers. They should not be too taxing. It'll be fun, and hopefully, I just hope you find these things beautiful. Let's see, so just reminders on what I want with homework. I think almost everybody except Lou knows this, but I've heard such great things about Lou that I'm sure it would happen anyway. When you do your homework, please just include an inkling of the problem you're solving. A rough problem statement so that I know you know what you think you're solving or whatever. You know. Communicate, make it pretty, thanks. The usual. So, all right, let's get rolling. Let me talk more about this history. Let me go back to my little history page because I don't have this stuff memorized like I usually have stuff memorized. So, complex numbers came because in the 1500s, there were kings. Like real kings, not the bullshit kings in England, right? Like the kings that had power and like made life terrible for people. The kings would have court mathematicians. They would have like can you imagine? I'm like the royal mathematician. And there was a couple, and some of the great names, I think Tartaglia, and you've heard this name, in Cardano. Yep. And if you do crypto, you know Cardano.
Nope. What?
Okay, cool. Then I won't talk about crypto, because that's just me. Okay.
I'm happy to hear about it.
So in the 1500s, there was Tartaglia, and he's an Italian dude, and then Cardano, I think, was also Italian, and then Del Ferro. And they were all working for kings. Different kings. And they were working on solving cubic equations. Like this is where math was back then. This was the hot problem of the day. Solve ax cubed plus bx squared plus cx plus d equals 0. Find all the solutions. So, in the process of this, let's see, who was the formula? This was, I redid the work here. Cardano. Cardano came up with a formula. So Cardano came up with a formula that said, first off, you transform that equation into this equation. So that's a transformation, and it's actually, you could figure out what it is. You replace x, you let x be replaced with like rho x plus phi or something like that. So you make a linear change of variables. You plug that in here, you figure out what rho and phi have to be to kill off this term. So the whole thing was make a sub, try to kill off the x squared term, and then get it here. And once they got it here, they had like all these techniques. And so Cardano came up with this formula. And you'll see why I can't remember this. I think you'll cut me some slack. The cube root of q over 2 plus the square root, that's all under there, of q squared over 4 minus p cubed over 27 minus the cube root of negative q over 2 plus square root of q squared over 4 minus p cubed over 27. So this piece is identical for both of them, it's just the sign changes on this q over 2. And that's, simply coming up with that is pretty impressive, I would say. That does not seem obvious to me at first glance, or third glance, or eighth glance, ever. It's never seemed obvious to me. So Cardano came up with this formula, but what you'll notice here is that there are square roots under here. And it doesn't take much imagination to imagine how this quantity could be negative under here. Make p a really big number, make q a very small number. This immediately becomes negative under here. So they were encountering these things, and they just kind of like worked with them and forgot about them. And they called them, the quantity that came out, so they ended up with these square roots of negative quantities. And this was very disturbing. Like people were such snowflakes about math. Is that like okay to say? Yeah, they were just like 0. Ah! Just like burn him. 0, what are you talking about? Negative, burn him. Everybody was getting burned for every freaking new number they discovered. So this was upsetting, but not to the point where people died. That was cool. We had advanced as a civilization. People weren't dying for numbers anymore. Wow, bravo, humanity. So they saw these and they just didn't make sense to them. And they coined the term imaginary somewhere along the way, which was really unfortunate. It's really unfortunate because they actually are quite real. This is like if you've done any physics at high levels, anybody did quantum physics? I mean, I haven't either. Quantum physics requires these numbers. Electronics, anybody done electronics? A little bit?
Yeah, you have to represent something as a square root or a negative.
Yeah, like I is in there, like crazy. So like this stuff turns out to be super essential, and then like I showed you at the beginning, like it also gives us great power, so it's not imaginary by any stretch of the imagination. So not much happened up until the 1700s, I believe, if I get to my notes in time. Yes. Even in the 1700s, Euler was doing crazy shit with these. Like Euler didn't understand. Euler's like our demigod, right? Like Euler's like done everything, every class. Euler did something. So Euler did this. Euler said the square root of 6 is the square root of -2 times -3. And then you know square roots of a product or the product of the square roots. We just do that kind of routinely. And now I've got this negative under here, so let me just do a little computation that you'll get more used to. It's -1 times 2, square root of -1 times 3. And then again, I can continue to break out those square roots. So and then we called that I, right? So it's I square root of 2, I square root of 3. Those become square root of 6 again. What is I times I? It's I squared. What's I squared? So Euler did that. That's not true. That's not true. Where do you think the error occurred? So this is like one of those cool puzzles where you prove 0 equals 1, and then it's like, what happened? Do you know the puzzle I'm talking about, the proof I'm talking about that 0 equals 1? Because you divide by 0 secretly. What happened here?
I mean, both of them are the square root of 6. Both of them square root of 6.
Correct. Oh, that's a great observation, Noah. Yeah, they both square to 6, absolutely. But there is this equality all the way through, alas. Well, I'll just tell you, you can't make this move with negative numbers underneath. You just simply can't. That wasn't something that we figured out till later, till we understood this critter a lot better. So Euler didn't even understand, 1700s. And then in the later 1700s, we had a huge breakthrough because people were like, what is happening? I cannot picture this. And Noah hit upon what was the big breakthrough. When Noah said, what was the first thing he said? It's a 2D number. So Noah said, oh, it's a 2D number. So these complex numbers, we have this real part, and plus this imaginary part. And they're like oil and water, they don't mix. And you get two descriptors for the number. So what a person argand, and maybe somebody else we actually know, because we won't know argand. Hamilton, Wessel, Argand, and Gauss, all at once, almost within like the same time period. So Hamilton, we know that. That's not like founding father Hamilton. That's like I did something Hamilton. No, I guess the founding father. It's not turned out the greatest, but whatever. Hamilton, Argand. Hamilton's work stood the test of time. Argand, and then Gauss. And then who else did I say? Wessel. Okay, there's a name nobody knows either. But all these people at the same time came up with this idea to take this number and turn it into a picture in the following way. Let the real part be represented by the x-axis. Let the imaginary part be the vertical axis. And so this number, a plus bi, could be thought of, and sometimes I'll put IB. You can, depending on what textbook you're looking at, what author you're looking at, it's either BI or IB. It's not wrong, because commutativity still holds, thank God. So imaginary looks like this, and you can associate it with a point in the real plane. So the real part is like the x-coordinate, the imaginary part is the y-coordinate. So this dot right here now represents the number a plus bi. And now I got a picture. So instead of the real number line, I have a plane, because as Noah said, I've got two pieces of info for each of these numbers. And now we can start having some fun. Let's just plot out a couple real quick so that we're sure we understand this. So we can graphically represent, and by the way, I'm still recording classes, so I will have this up for you ASAP. We can graphically represent complex, let's go complex numbers. A plus bi. So let's do a couple. What about I? So let's just draw out here. Where's I? Is there a real part? Do you see a zero? There's no plus, right? So there's an unspoken 0 plus I. Where do I put that point? On the y-axis, yeah, how far out? 1, beautiful, because there's an unspoken 1 in front, right? So this is a 1i, so it corresponds to 0, 1. So it's this point right here. That's I. Where's negative 1? How many units? Yeah, beautiful. There's negative 1. Here's 1. Here's negative I. Is this making sense? Sound legit? What's this number right here? 1 plus I. Quite lovely. What the fuck? I thought I turned this off, but apparently not. What's this number here? 1 minus I. Very nice. Lovely. Where's 0? Thank you. Good job. Thank you. That's 0 right there. Cool. So now we can express any complex number as a dot on the plane. And that, boy, you're going to do this all the time, constantly. So, what comes next? Let's talk about some of the basic operations of the complex plane. So this plane, so remember this, that R, that beautiful R, which I love, can you tell I like writing that? Yeah. It's got love in it, doesn't it? Yeah, that's the real numbers. And then I also love C, which is the complex numbers. And there's some crazier versions of this. There's like the Hamiltonians. You ever heard of those?
Those are the 4 ones, right?
Yeah, those are the 4 ones. Look, we're not going to study this, but I will just say there's the Hamiltonians is the collection of all things that look like this. And this I squared is equal to J squared is equal to K squared is equal to negative 1. So they all have that property, but they also then have this property that I times J equals K, and J times K equals I. Have you seen this? Yeah. Maybe in algebra. You don't remember where? No. Probably one of your CS professors just talking about anything but what you needed to learn. So then K times I is J. But when you go backwards, so here like IJ is K, but JI is negative K. So it's a really interesting number system. We're not going there. If you're ever in Scotland, I believe Hamilton inscribed these as he was walking over a bridge, and they're still there. What a nerd. What are you doing, dude? You writing your name? No, man, I came up with new numbers. Get them down. All right, let's talk about just some basic properties and qualities of these numbers. Oh, so glad to be here. So happy. This is a very old fogey chair. It should be a rocker. Okay, so usually, we usually use X and Y for like real numbers. But in this class, we use like Z's and W's for complex. So this, just like culture, math culture is we use Z's and W's for complex numbers. So I might say something like this: Z equals Z1 plus Z2I, and W equals W1 plus W2I. So I've got 2 complex numbers there, Z and W. And if I plot them out, I don't know what their components are, but let's just pretend we do. So there is Z, and then maybe we can make W down here. So there's W1, there's W2. So I'm talking about this number for W. Is this sound okay? Am I going the right pace? Okay. And always please stop me. I think Lou, just so you know, always stop me.
Okay.
We never move forward without understanding in our class. Or clarifying at least. Sometimes understanding takes days, right? But we try to at least get things better. Okay, so when I add two complex numbers, when I add z plus w, I just, well, let's write out what that would look like. So the cool thing is, this I is like a grouping mechanism. Imaginary things pool together, real things pool together. So you can kind of think of it that way. It's just kind of like you would add vectors, right? How do you add vectors in linear algebra? Component-wise. So this is going to be z1 plus z2. That's my new real part. Plus oh, sorry. Yeah, I did screw up. Plus w1. And then z2 plus w2 times I. Let me do a quick example. So if I said take -1 plus 3i plus 1 minus 2i, what's my sum there? Beautiful. That plus that is 0. That plus that is 1i. You don't have to put the 0 ever if it's a pure imaginary. So pure imaginary means no real part. Pure real means no imaginary part. Good news. We can easily change this to our subtraction routine. So if I put minus there, then I subtract the components. So addition is component-wise, subtraction is component-wise. So let's do this one here. If I have -1 plus 3i minus 1 minus 2i, could you do that real quick for me? Now we're finally getting to where you don't have to just listen. What we got?
-2 plus 5i.
Neat. Very cool. Very cool. Let's go to the picture and take a look here really quick. So, if I have this number here, which is z1, w1, so this is z1 plus w1i. And then I have another one, let's say it's like right here, and that one is z2 and w2. So this number here is z2 plus w2i. Let's draw a little picture here. So this one, and you're going to want to draw this picture in the future anyway. I can almost think of them as vectors. And when I add them, look at what's happening. I'm adding z1 plus z2, so that's going to add this distance here onto that one, and just kind of like shift that over. It's going to shift this over z2 units, so over here. And then when I add w1 plus w2, it's just going to shift this w1 up a point. And so what you're going to see is a parallelogram, just like with vectors. And that number there is the sum at the tip of this parallelogram. So this is the sum right here. Do you remember how when you'd subtract vectors, how that relates to this rectangle? Or this parallelogram, sorry. Do you remember how that worked? Let's take a look. Let's pick a couple numbers and let's do an experiment. So let's pick some numbers that are kind of like this. So let's do like 3 plus 1i minus, and then let's do 1 plus 3i. So they kind of have this vibe of those things. And then, you know, we work that through, so it's 3 minus 1 is 2, and 1 minus 3 is negative 2, so 2 minus 2i. All right, now think about where this is in the plane and like, how does that relate to that thing there? So let's take a look. So 3, 1, 2, 3, 1. So there's 3 plus I. And then here is 1 plus 3i. Now notice that the sum would be 4 plus 4i, which would be just right up here. But I'm subtracting, so I've got 2 minus 2i, so gosh, let's see, that's 2 over and 2 down. So there's 2 minus 2i right there. How does that relate to those two numbers? Luke.
So like if there were vectors and then each of the points that we have is the tip, then it's like if you took the tip of one and put it onto the tip of the other one, so then the beginning of it is where we're ending. That's the subtraction.
Yeah, like here's the tip of the arrow. Yeah, exactly. So what Lou's saying is that when I subtract these numbers, it's like that vector shifted down to 0. So look right here. What does this look like between these two? It looks exactly like this, just shifted down. So that's kind of the relationship there. It's weird that it gets shifted, but it does relate to that rectangle or parallelogram in that it's the same length and same orientation. It just stems from 0. In the end, probably the addition idea graphically is the one that's going to pay off the most. This will pay off a little less, probably, maybe, if at all. Things get really weird when we start multiplying. So that was addition and subtraction. That's chill. So let's do multiplication. Because this is where we start to see why having the plane and a representation is going to be helpful. So let's say z equals z1 plus z2i. W equals w1 plus w2. And I want to think about the product of those two. So let me write it out, and then let me ask for guidance from my wise friends. What do you think? How do we do that?
I'm feeling foil.
You are, oh man, I feel the foil too. Isn't it amazing how foil like gets you through even like graduate level mathematics?
Definitely my dog passed away too.
Oh wait, what? Oh God, no, okay. Oh God, no.
No, it was a joke.
It's okay.
Oh, it's always there for you.
You got, no, it's fine, God, it's good, it's good. It's just like, I instantly want to hug
My
you.
dog didn't, or it did with those years ago. I'm not sad.
Okay, good.
Oh my god, that escalated quickly.
That's not, saying I'm not sad is not the best way to convince people that I'm happy, but I am. I'm doing okay.
He seems okay.
Thanks for your concern.
I think we're cool. We're just
See,
concerned.
When we're doing math and then someone like says something not exactly related, I just get so confused. What's happening?
She gets whiplash from trying to keep up with the conversations.
No,
I'm just glad you're okay and your
Yeah.
dog is okay.
Yeah.
Well, he did die years ago.
Oh! I'm just kidding. Do this. Foil that shit.
Oh my god.
Thank you.
Please. Break and foil it.
Foil that shit.
A dog named Foil. Me, my Goyle, and a dog named Foil. I'm gonna write that country song.
Oh my god.
write this in true FOIL form. Wait, that was, that's Fleo or something I'm about to do. Usually tack the I either at the start or the end. Don't leave it tangled in the midst of a computation, at least that's the final version.
Your first term,
Yeah.
W.
Thank you. Good to have folks like you
And a
around. And a one. Anything else fucked up? That looked good? Yeah. Cool. Yeah, thank you. So, once you do computations, replace every power of I with either, well, we'll get to that, but simplify all powers of I as far as possible, either down to a -1 or a negative or positive I. Or a 1 as well. So, this is just going to become -1. And that means I'm going to have a real part. Then I pull together the real and the imaginary. So I'm going to have Z1, W1 minus Z2, W2. That's my real part. And then the imaginary part is going to be Z1, W1 plus Z2, W2. I. Pretty weird, right? Kind of a weird formula. Like when I look at that, it looks beautiful and interesting, but it provides me with zero intuition. Anybody, maybe you know, you all have like fresh views on things. I'm a stale old man. I mean, old man is one of my freshman cartoons. Oh man, she said I was.
You're choosing one on the second pair.
Say that again. Dot product D. Yeah, is that what you said?
Z1, W2, right?
C1, W1.
That's
Oh
that's
wait,
an
oh
action.
thank you,
Yeah.
thank you Noah, thank you. Did I totally, and then this is screwed.
Your thing up there is
Okay,
good.
this, I just copied wrong, okay, I copied
No,
wrong.
not, but, yeah, okay.
Yeah, thank you.
Too many subscripts.
It's a lot of
It's
subscripts.
so.
Could have gone for fewer subscripts probably to
Yeah,
day one.
but yeah, that does not tell me anything aside from.
Yeah,
this.
yeah.
A lot of math that I've saved for later.
Yeah, it's like, yeah, and you can see like, oh, dot product, oh, related to dot product or something. But it's useless. It really is. It's quite useless. I mean, you get your numbers multiplied. You'll be done. You got an assignment that says multiply two complex numbers together. Voila. Done. For example, what if I multiplied 1 plus I times 1 minus I? What do we get?
Get just 2.
To get a real number, right? And cool, and it's right here. So here's the product. Here's the two originals. Here's the product number. Kind of looking like that diagonal, but not necessarily. Let's do another one. Let's do 1 plus I times I. So let's do 1 plus I times I. -1 plus I, is that working out? Make sure you're getting -1 plus I. But that is clearly not on the diagonal here. Doesn't seem very much related to these two at all, unless we see a different things. There's a different way to look at what's happening here, and it's gonna like totally blow your mind, I believe, in the best way. We need to represent our complex numbers a little differently. So to gain real insight, and this is what the drawing of these did for people. It provided this deep, deep insight into the nature of these numbers. To gain real insight, we need to move to polar form. Remember how you did polar coordinates in like some class, and then it was like, what do you use them for? You use them for polar coordinates. Duh.
You like drawing circles?
yeah, circles and lemniscates and cool things like that, right? Little hearts, you can make a cool little heart and stuff. Matthew Valentine's things, but this is going to actually do something for us. So here's the idea. So given z equals, let's just do a plus bi. I've had enough, I'm sure we've all had enough subscripts for one day. We can draw it. So we draw it, and usually when you do these arbitrary drawings, you just pretend like it's in this first quadrant, like so. And then you label it just z. So. We can notice that every number in the plane is described by not just two rectangular pieces of data. It can also be described as, here, let me just go through this. I'm just going to do this. You probably already see where it's going, but I don't care. I'm going to do this. So to get to Noah, I can think of this. To get to Noah from here, I walk forward 2 steps, and then I turn at 90 degrees, and I walk forward however many steps. And that's Noah's coordinates relative to the origin over here. Here's another way I could describe getting to Noah. I could say, rotate 75 degrees. Walk forward this distance from here to Noah. Notice they both get me to Noah, but they're 2 very different ways. This is like nautical almost, right? You're out in a boat or like flying an aircraft, and you just say, how far to the left or right do I turn? And then how far do I go in that direction? That's polar coordinates, and that's what we're going to do. So to describe the z, I could say there's this distance r that represents how far I travel from the origin. And there is a distance, an angle theta that we'll use radians for. I said degrees, but only because I can't convert 75 degrees to radians quickly. So this theta is in radians. And this r equals the distance, let's say rads from standard position. And standard position is just the positive real axis. And then r is the distance from 0. So let's see, how do we have that? All right. So let's draw a little right triangle there, and let's relate a and b to theta and r. Hey, help me out here. How does r relate to a and b? Yeah, good old Pythagoras, right? There's 2 things that get you very far in math, FOIL and Pythagoras. Cool. What's theta?
Inverse. Some.
Yeah, that's good.
Inverse tangent of b over a.
Beauty. Arctan of b over a. Yeah, absolutely. Love it. And we could do cosines and sines too if we wanted to incorporate that r, right? We could do that over r and so forth. So that is quite sweet. Now, how do I move back? If I, well, here actually, how do I describe A in terms of R and theta? And then B, let's do B as well. So do the trig. Here's the triangle, there's the hypotenuse, there's the angle, what's this distance here? SOHCAHTOA, right? Yes.
Yes. I
Yes.
believe so.
SOHCAHTOA is your friend here. Another thing, gets you far. Like 3 things. That's all you need for a PhD.
No, I'm set then.
You are set, yeah. There's a strong stomach lining too.
You,
Lots of big box of Kleenex to cry into.
you're not making being a math professor sound very fun.
Oh, the professor part is great.
It's the getting there.
It's the getting there that sucks. Especially when you have a bipolar advisor.
Oh no.
Yeah, who's a maniac on top of it. Can anybody give me the formula here in terms of R and theta?
R cosine theta.
What about this one? Yeah. And let's just talk about that really quick if you were having trouble deriving those. Don't forget, SOHCAHTOA, so sine is opposite over hypotenuse. Just to help you remember this stuff. So the sine of theta equals the opposite side, which is B, over the hypotenuse, R. So now look, that tells me that B equals R sine theta. And similarly for the cosine. So just using SOHCAHTOA, we can grok that information. So, ho, now look, I'm going to take this and rewrite it like this. So I have this number in rectangular form. And I can write it in polar form as R cosine of theta plus I R sine of theta. I'm starting to get a little sloppy here, so let me get an eraser and get that shit out of the way. So sometimes, and quite often, we'll factor that R out. We'll write it like this, and then we'll do a shorthand because this is like redundant. Once I know this is what is happening here, I would just write this, so I'm going to put triple equality here just as like, we can notate this as R cis theta. And you read that as cosine plus I sine of theta.
Wow.
That is going to be your friend. Now. All right, let's do something even funner. Let's come back to this with this new insight. So, instead of saying this, I'm going to say Z equals R1 cis theta 1, and W equals R2 cis theta 2. Can you feel like the plane like kind of coming off the ground a little bit? The wheels, you know like you're in the plane and you're like, are we off the ground yet? Yeah, we're good, we're lifting. So I represent these numbers in polar form. Remember what this means. It means R times the quantity cosine of theta plus I sine of theta. So Z times W is the product of these two things. And we can even group together the R1, R2. This is our new radius. So the lengths actually multiply like normal real numbers. The radii, the distance from 0, still just, it's like normal real number multiplication. But now we've got to write some stuff out over here. So this is going to be cosine theta 1 plus I sine theta 1 times cosine of theta 2 plus I sine of theta 2. Foil, anyone? Can you FOIL that out for me and simplify it into a complex number, please? Then, if you're really feeling like ducky, whatever that means, simplify simplify it as far as you can. And that'll give me a great chance to go pee. I'll be right back. Been a long morning in this room. Hey, I was just thinking about you. That was nice. Thank you. I love it. It's day one, you know. Thank you. Yeah, that's like you. That's like fancy. Yeah, fancy. Good too. I go, wait, this is one of those obvious. I don't know, but that's nice. You turned me on, and that's all I asked for. Just, I like to work with those. How are you? Good? Oh, everything's okay. We're our summer with mom, but thank you. Not good, but it was a bad summer for that, but it was still a great summer for my car. Good.
Yes, he's seen me.
Yeah. Yeah, oh yeah, some of your friends are, yeah. Guess I better get cracking. Are you starting to see any formulas you may or may not recognize? One I had up earlier.
I feel like there's a half angle.
What were you- Yeah, kind of related. What were you gonna say, Lavina?
I recognize them, I can't recall them.
Yeah, fair, but you know, you're like, that's something. So that times that first gives me that, and then I'm just gonna do the L first because the L always becomes the real part. So that'll be minus because of I squared. Yeah, and then, oh wait, and then this is all times that. That's just the real part, so double bracket, plus I times, and then we get the mixed term. So we've got cos theta 1, sine theta 2, plus cos theta 2, sine theta 1, and that's got, they each have, oh, I already got an I, one I. Does that look legit? You might have different orders, you know. What can I do? Because there's something really gorgeous I can do next. And it was a formula I put up earlier at the start of class. I said, can you prove this?
Sine of theta 1 plus theta 2 for the second one?
Yeah. This is sine of theta 1 plus theta 2. Huzzah. What do you think this is? Let's play the game because we're students and we know how to rig the system and work from patterns.
Is it cosine of theta 1 plus theta 2?
It is. This is cosine of theta 1 plus theta 2. Let's write it. So, z1 times z2 is product of the lengths from 0. I'll give a better term for that soon. And then, cis theta 1 plus theta 2. Add the angles, multiply the lengths. What was this angle here?
45 degrees.
45. we'll stick with, we'll just do degrees for fun. What's this angle here? 90 degrees. What's this angle here? 135. 90 plus 45. How long is this line?
Square root of 2 over 2?
Actually square root of 2, because these are ones. You're thinking of,
Oh,
you're thinking of
On
the,
the
if
scale.
we had set this to length 1 here. So,
Okay.
right, this is 1, so that's root 2. How long's this? 1. How long's this? Root 2. 1 times root 2 is root 2. This is what we gained. You see that multiplication of complex numbers is just simply multiplication of the magnitudes and addition of the angles. And that's how you get your new one. And that is quite a beautiful thing. So let's multiply a few numbers. Let's see, what do I got here? Blah, blue. I don't have any problems made up, so I just gotta mix them up. God help you. Like, no, I do. It's okay. Everything's safe. I got some stuff. Found it. Yeah. So here's Z1 is root 3 minus I, and Z2 is 1 minus root 3I. Step 1, please plot these out. What is root 3 approximately?
1.7?
1.7 works good for the way we can draw, right? Like, we don't need the 0.7, the 0.03. I don't. So it's like, you know, a little less than 2, somewhere between 1.5 and 2 when you're estimating on your drawing. You know, rough. Not gonna be launching any missiles based on the work we do in this class. Never. I hope you never have to launch a missile. So let's convert these. Can you please convert these into polar form? I guess that's my next question. So convert, these are rectangular. Can you write them both in polar? Got a 30-60 triangle, like, loving up the board. I would use negative angles, probably. You could do a full sweep around, but I would say like negative pi over 3 or pi over 6 or whatever. Hint, hint. One of those, do both of those actually.
Oh, thank you.
Yes. let me just put up a friend you're gonna want in this class. Kind of nice to have that unit hypotenuse for various sundry reasons.
that pi over 0 for the angle?
Sorry, no, that's, oh, that would be a bad day. No, that's a 6, Nathan, my friend, sorry. Yeah, just slip into a little division by 0 to like blow everybody's mind. Anybody, I'll come around. How's it going? Anybody thinking they got it?
No, I'm.
Okay, no. Yeah, okay, cool. I think the problem is mostly just like trig knowledge, right?
Yeah.
I'm kind of researching right now.
Yeah. That's okay. I knew it would be.
Inverse tangent is not fun.
No, don't do inverse tangent. Good God.
That's how we find theta. Well, yeah, but like also I want to pretend I did inverse tangent.
No, look. So let's look at this triangle here. So look, see, we got to find Z1, we need to understand this, right? And then let's see. So this was square root of 3. And this is 1. So what's that hypotenuse?
2.
2. Square root of 4 is 2.
Okay.
Yeah, that's cool. So now we've got the radius, right? That squared plus that squared is 4. Square root is 2. This is a 30-60 degree triangle. It's that one down there, just where everything's multiplied by 2, right? If I scale all this stuff by 2, I've literally got that triangle up there. So now I just have to like lift it out of the board and flip it and do all kinds of things. But what is this angle here? That's 30, so that's pi over 6. What's this angle here? 60, so pi over 3. Beautiful. So, this angle here is pi over 6. So, and this radius is 2, so this first number, Z1, is 2 cis pi over 6. Negative pi over 6, because we went down. So that's a negative pi over 6. This one down here is just the same triangle, oriented differently. We've got root 3, negative root 3. I've got a 1, so I know that's 2. So what's this angle? Pi over 6. There we go, now we're talking in radians. I love it. This is pi over 3. So, see that triangle right there? That's this one here. What was that sweep?
Negative 5 pi over 6.
That's too much.
Pi over 2.
That's too much. Negative pi over 2 would take me all the way down here. What plus, this, the pi over 2 is this, right? That's 90 degrees. Oh. What's this little chunk right here? Because that's what I got to sweep.
That's pi over 3.
Pi over 3.
So the total is pi over 2.
Correct. So this is sweep of pi over 3, because this is pi over 6. This is pi over 3. So this number here is 2 cis negative pi over 3. Day 1. Cool. Good. Yay. We're not done yet. Hold on. Now I want to multiply these mofos. And then we'll be done. I got like 45 seconds. Holy shit. So Z1, Z2 equals. Okay. Z1, Z2 equals product of the amplitudes.
Yes.
2 squared. Cis. What angle?
Negative pi over 2.
Yes! So let's put in negative pi over 6 just so that you have this for your notes. So just add those angles. And that is 4 cis negative pi over 2. Oh my god. Negative pi over 2 means start here, sweep down 90 degrees, and go down 2 units. 4 units. So negative 4i is the answer.
The angles are a lot easier to visualize the amplitudes when multiplying.
Yes.
on the keyboard.
All right. Have fun. Start early. Start early. I become a super badass. I'm like brutal. No, like Sydney's like she doesn't even believe it, and she shouldn't, nor should she. But so if this homework is due Monday, let's try to ask questions before then, right?
Hopefully.
Because I'm not available.